Hello everyone. We're finally at the part of the course where we're ready to start using GLSL. So we're going to be using a different kind of programming language. And in particular, we're going to be programming the graphics card on your computer. So if you're watching this video right now, your computer has a GPU, graphics processing unit. And this is a chip that's specifically dedicated to drawing colors on pixels on your screen. And it's got, well, the ones these days sometimes have thousands of little processors in them working at the same time, each to draw a different region of your screen. But to start off with an example, let's first see how we would do a particular task that a GPU might do without the GPU. Okay, so the coordinate system that we use, by the way, to draw pixels on the GPU, the lower left is -1, -1, so x is -1, y is -1. The lower right is 1, -1. The upper right is 1, 1, and the upper left is -1, 1. So that's the coordinate system we're going to be working with here. Okay. Now let's look at the following problem. So what if I had a triangle and the vertices happen to be at 3 of the corners? So A was in upper left, B was lower left, and C was upper right. And let's say that I made A red, B blue, and C green. And what I wanted to do was to interpolate all the colors in between. So something in the middle here should be a mix of red, green, and blue. If I'm over at this vertex, I should be all green. If I'm halfway in between these two, it should be a mix of green and red. Now maybe that's starting to sound a little familiar. So now we're going to use barycentric coordinates to do this. Okay. So if we pick a particular point here and we say it has barycentric coordinates alpha, beta, and gamma, we can then solve for a color, which is alpha times the red. So my barycentric coordinate for A times the color at A, which is red, plus beta times blue. So red, green, blue, so 0, 0, 1 is blue, plus gamma times green. Okay, and we're going to have to do this for a lot of pixels. So this particular image, I zoomed in, but it was, I believe, 600 by 600 pixels. So that's going to be 360,000 pixels. So we'll have a loop that goes through 360,000 times and computes these barycentric coordinates over and over again and does the average. Now, does that sound like it's going to be slow? Like a loop that goes almost 1,000,000 times and keeps doing these triangle areas over and over and over again? Yes, that will be slow. So if I start to move these points around or change their colors, and I want to change the image, I'm going to have to start from scratch and compute this thing over again. And that's going to be really not interactive. But one thing we notice is, look, a point here, the calculation I do for that point doesn't depend at all on the calculation that I do for this point or this point. They don't depend on each other, so they can be done in parallel. So I could choose, if I'm doing a loop, I'll have to choose an order to do them in. But I don't have to do that. If I say give some of them to one of the cores on my processor and the rest of them to another core, then I could do them faster. Now this is exactly what the GPU is designed for. So the GPU is going to have a bunch of little cores, each of which is responsible for processing just a little section of this. So that GPU will figure out all the pixels here in that core, and then there's another core that'll do these pixels, and another core that'll do these pixels, and those cores can all run at the same time. So because these things are independent, we can run them in parallel in the GPU cores, and it goes much faster. So this is what I'm going to show you now. Okay, so we're going to start looking at a new kind of programming language. And let me first just show you a little bit of JavaScript first. You don't have to worry too much about this stuff. I'm taking care of a lot of things for you. What I really want you to focus on is these buffers here. So this is called a position buffer. This is going to store the coordinates on my triangle. So I see up here, okay, so I've got -1, 1, I've got 1, 1, and I've got -1, -1. Okay, so this is just going to store those 6 coordinates. And I'm also going to store these colors here of each one. So remember the one in the upper left, -1, 1 was red, so 1, 0, 0. The one in the upper, or let's see, this one is, yeah, the one in the upper right is green, so that's going to be red, green, blue. And then the one in the lower left is blue, so it's going to be 0, 0, 1. Okay, so these are two parallel arrays that I've set up. One of them holds the coordinates, and one of them holds the colors. Now, I haven't really done anything super new yet. I'm just specifying this information in flat arrays. So x1, y1, x2, y2, x3, y3, just right after the other. So it's a one-dimensional array, not a two-dimensional array. That's what a buffer is. Okay. And same thing with the colors. The only thing that's maybe a little different so far is I say float 32 array. What this means is everything on the GPU actually is a float. You can't really use double. So you only have 32 bits to work with, but the result is you can store more pixels. Okay, so you don't have as much precision, but you don't really need the precision, right? We've been rounding around and we're never quite exact. So floats are fine, but we have to tell JavaScript that we're using floats. Okay. And there's one more thing here. These are the indices. So the GPU is very, very good at doing a very simple thing, which is drawing a triangle, which is why we're starting with this. So GPU is really good at drawing triangles. If we tell it what triangles to draw, it can do that really, really fast. So what we're going to say is, okay, look, I'm giving you these positions and I'm giving you these colors. What I want you to do is make a triangle that does the whole barycentric thing between these three vertices. So I only have 3 here, so it's not that exciting, but I'm saying that index 0, index 1, they come in 2. So the 0th point, point 1, and point 2 are going to make a triangle, and I'm going to draw that triangle. Okay. And then I have a function to set up the buffers and actually move them to the GPU. You can look at that if you want. In the starter code, it's in this file shaders.js. And it's this function here. So you can look at the actual, so we're using something called WebGL to interact with the GPU, so you can see how this stuff is actually sent over to the GPU. But you'll never have to do that in this course. I've taken care of a lot of the ugly stuff for you, so you can have fun with the fun stuff. Okay, so anyway, those are the buffers that's what we're going to need to tell the GPU, and it gets sent over to the GPU. Okay. And then eventually we go to draw the triangle. So I put that all in this function I call render. And what we just do is, again, you don't really have to worry about this, but it's just saying, hey, these are the buffers that I'm going to use. And then the key thing is I want to draw a bunch of triangles. That's this line here. Okay. But now here's the part of the code that I really do want you to focus on. So how do I write code on the GPU? So that's the next thing we're going to look at. So there are so we're going to write something called shaders. So a shader is a program that executes on the GPU. The reason it's called a shader is because it literally shades in triangles. That's what it does. That's its job. But you'll see as we go on, it's amazing what you can do just by shading in triangles. Okay. But we're going to start with a simple example first. So what we have for a shader is actually 2 different programs that work together. The first one is called a vertex shader. And I have the convention where I always end it with .vert. The next one is a fragment shader. Okay, so I'll explain what these 2 things are. Actually, before I do that, though, I'm just noticing under Windows here, this is a good teachable moment, I should look for an extension in Visual Studio Code for GLSL. So this is the language for writing shaders. So I guess I'll install this extension here. And then it should actually do syntax highlighting. Okay, good. Now I've got those colors. Excellent. Okay. So you should definitely do that. That'll help. It makes it look nicer as you're editing it. Okay, anyway, so we've got 2 shaders, a vertex shader and a fragment shader. So what a vertex shader does is it runs on each vertex. Okay, so remember in this example I have 3 vertices, right? 1 for each side of the triangle. So it's going to do something to each one of those vertices. the vertices can come with a lot of information. So in this case, they only each came with 2 pieces of information. The first one is a position, and the second one is a color. Now the syntax here is a lot like C++, but it's a little bit more restricted, as we'll see as we go on. But essentially it's C++ syntax. But there are also some special types that are built in. So we automatically have basically everything that was in GLMatrix is built into GLSL. That's the reason that we're using GLMatrix. Even though it's kind of a pain library, now you're kind of familiar, you know the types that you can use. So vec2, okay, this is a vector with 2 components. Vec3, this is a vector with 3 components. So our position that comes in, this is the vertex of the triangle. That's 2 coordinates, right? The color that comes in is actually 3 coordinates. It's got red, green, and blue. Okay, and so what we do is we have to set up, there's a special variable in each vertex object called a GL position. And this is actually a 3-dimensional position, but in homogeneous coordinates of this vertex. We're just dealing with the plane for now, putting a triangle on the plane. So what we're going to do is we're going to wrap in this x and y position. We're going to make z is equal to 0, and we're going to make this 1, right? Because it's for homogeneous coordinates. Okay, now notice that's some kind of nice syntax right there, right? I didn't have to say I could have said vec4 a position.x, a position.y. So those are the components. So I can access the components of these vectors with .x and .y. I could have said that, but actually GLSL is super slick, and if I put a vec2 in the vec4, it just unwraps the first 2 coordinates and makes them the x and the y. And then we got the z, and then we call it w. But yeah, this is the homogeneous coordinate, okay, which is usually 1. But we'll see. In a few weeks, it's not always 1. Okay. All right, so that's the basics of a vertex buffer. It just takes in information about each vertex. So basically, on the example we have, this is only going to be called 3 times on the GPU. Okay, but you could have humongous triangle meshes with many, many vertices, right? Like the mesh of my face that you've been working with. And then this vertex buffer would get called many times. Okay, but in most of the examples that we're doing in the shaders unit right now, these vertex shaders are going to be pretty simple. They're just going to be there to set up the vertices and to pass on information. So here's where so notice this thing called an attribute. So this is, the attribute is something that comes per vertex, okay? So every vertex has a position attribute and a color attribute. Now we're going to move on to something where the vertex shader actually talks to the fragment shader, and then we'll talk about what the fragment shader is. So now you have this keyword varying. So here's where the barycentric magic happens. So what varying says is, I want you to take the attribute. Well, okay, so you actually have to assign it something. So if I say the color is equal to a color, this looks like not very interesting. Am I just copying directly what the color was at a vertex? Not exactly. So here's the deal. If I initialize a variable here called vColor, and then I go over to this fragment shader, notice I have the same variable here. Okay, so what a fragment shader is, and I have it written here. A fragment shader actually operates at every pixel. So this thing gets called many, many times, even if there are only a few vertices. And you can actually, it automatically interpolates. If you're drawing triangles, it knows how to interpolate using barycentric coordinates the value that you give it. So when I say vColor equals a color, what I'm really saying is, okay, look, at a particular vertex, it's this color. And then this vertex shader will be run at other vertices as well. But in the fragment shader, this is going pixel by pixel. So you're going to be somewhere in between vertices. And we're going to make this vColor be the barycentric interpolation between the attributes of the vertices. Okay? And this executes like boom. Okay? So let's look at it. So I have just a very simple main to get this thing started in Triangle HTML. So if I open this with a live server, look, there it is. It took no time at all. You know, I can if I change. Let me get these side by side here. I could change the positions in the position buffer. So I could make the upper left be a little bit lower down. Maybe I'll make it a 0.5. Okay, see, look, you know, it drew in no time. Which should be no surprise. I mean, you have insanely complicated movies and video games that render real time. But so it's not surprising we should be able to do a triangle fast. But the point is that, look, we're actually doing a whole bunch of barycentric interpolations on the GPU at the same time across different cores. So yeah, I could change the color too. Maybe I could make the upper left white. Okay, so see that interpolation now. I could also, I mean, this is just the buffers that I'm sending. I could modify the fragment shader or the vertex shader themselves. Maybe I could say, you know, if the color dot x, so if the red component is greater than 0.5, then I'll clamp it at 0.5. So I'll say v color dot x equals 0.5. Could not compile shader. Why is that? L variant requirement. Oh, can't modify variant. Okay, yeah, we have to do something else. Well, we can defend. Yeah, so you'll see a lot of these. It's very weird, this programming language. But okay, so what I'll do is I'll make a temporary variable. I'll say float. We'll say the red component equals the color dot x. If the red component happens to be greater than 0.5, then I'll clamp it at 0.5. And now what I'm going to do is I'm going to send the red, the green, and the blue over. So I'll make temporary variables for green and blue as well. Okay, so now notice the red got a little darker because I didn't allow it to ever go above 0.5. And actually, I could say, look, you're just always. Here's another thing to point out. Okay, why didn't this compile? You're going to make this mistake many times. That's why I just made this. I make it almost every time I write a shader. It says on line 11, wrong operands. No operation greater than exists that takes a left-hand operator float and a right-hand operator int. And then same thing with the assignment. So it's yelling at me about these two lines here. And the reason is, if, okay, R is a float, you have to always, even if it's 0, you have to have the 0.0. Even if it's an integer, you always have to have 0.0. All right, anyway. So now I clamped the R at 0. Actually, let me even, I guess what I can do is I can say if red is greater than 0.5, then I'll change green. How about that? If red is greater than 0.5, I'll set green to be 0. Let's see what that looks like. Okay, so see we get this weird thing where as soon as you get close enough to red, it just totally loses its green. I could actually make it lose the blue as well. Okay, so now we see this triangle kind of sticking out here. All right, cool. So these are the basics of shaders. So you've got two shaders. Vertex shader, which takes in these vertices from these buffers. They have attributes that come along with them. In this case, I just passed along an array of positions and an array of colors. But you can pass along many more things. And then you can actually pass by barycentric interpolation. You can pass some of these attributes over through varying variables to these fragment shaders. And these fragment shaders are per pixel. Okay, so that's how it all works. So I'll do just a quick exercise to make sure you got that, and then we'll keep moving.